All right, in this section we're going to learn how to solve some exponential and logarithmic equations. We're going to start with a pretty simple one. Let's say we want to solve this equation for x. 2 raised to the x power is equal to 8. This one we can solve really just by inspection. We can observe that 8 is a perfect power of 2. The solution to this is x equals 3 because 2 cubed equals 8. Now, we've got kind of lucky with that problem. 8 is a perfect power of 2, but if I changed it just slightly, what if I want to solve the equation 3 to the x equals 8? 8 is no longer, is not a perfect power of 3 the way it was for 2. So solving this by inspection isn't really possible. I think the best we could do is say that it's bigger than 1, because 3 to the first is 3, but it's less than 2 because 3 squared is 9. That's sort of the best we can do as far as like taking a stab at a guess. It's between 1 and 2, and probably pretty much closer to 2 because 8 is pretty close to 9. The way we can get a precise answer is to use logs. Anytime we want to solve an equation where the variable is trapped up as an exponent, we're going to take the log of both sides so we could take that exponent, bring it down in front, use that property of the exponents. So in this case, and you could choose any base you want. So let's say here I choose to take the common log of both sides. That's the log base 10. Then my equation looks like this. As long as you pick the same base for both sides, you could take the log of both sides. Now I'm going to use that property that says if I'm raising something to a power inside the log, I can grab it and bring it down in front as a factor. So I get x times log 3 is equal to log 8. Now, log 3 and log 8, those are just numbers. They're constants, just like 5 and 2, only they're sort of couched inside these logarithms. And the point I'm trying to make here is that solving an equation that looks like this is just like solving an equation that looks like, 7x equals 132 or something, right? Like I have an x multiplied by a constant equals another constant. If I were to solve that equation, it would take us about 2 seconds to realize, oh, I just got to divide both sides by 7, right? And then I can get my answer. The same thing holds over here. Log 3 is just a constant, so I'm going to divide both sides by log 3. So as an exact value, x is log 8 divided by log 3. And the reason we pick a log like the common log or maybe the natural log, sometimes we'll use the natural log, is because those functions, the common log and the natural log, are built into our calculator. And the advantage to that is that I can actually get an approximation. So I'm going to go ahead and plug this into the calculator, get an approximate value. So log 8, really important here, I'm going to close those parentheses and then divide by log 3. And I get 1.893 approximately. So there's our solution. We can do a quick check. And if this holds out, again, I'm going to check in the original equation. So if this holds out, then if I take 3 and raise it to the 1.893 power, I should get something very close to 8. I get 8.002, so that is very close to 8. Before I do another one, sometimes people get a little uncomfortable with, this concept of just dividing both sides by a log, or like remembering the fact that, log 3 and log 8, they're just constants. And sometimes people are more comfortable just working with decimals. So it is okay if at this point here, let's say you get to this point in the equation, if you just want to throw log 3 in your calculator and get an approximation for that value, and log 8 in your calculator. So log 3 is equal to 0.47712. I don't want to round too coarsely because that can throw off my answer. So I'm going to grab several digits of this, 0.47712. So the left side, 0.47712x, and then log 8 is 0.90309. And looking at the equation, looking at this equation sometimes is a little simpler for people to think about solving. And so here, of course, we would just divide both sides by 0.47712. And let's see what we get here. 0.90309 divided by 0.47712 is 1.893. So same thing, which is as it should be. So we're going to do a few more problems, right? This was kind of a simple one. We just had to take a log of both sides, and then we're pretty much ready to solve. Remember that the whole point of taking a log of both sides, we start with an equation that has no logs in it. We're imposing the logs ourselves because there's some property of logs that's going to be helpful for us to use. So let's try another one. Here I want to solve the equation 3 raised to the x minus 2 power equals 5. So again, I can just see that my variable is trapped up as an exponent on the base 3. And we are just going to take a log of both sides. This time I think I'll take the natural log. And really, you could take the log of any base you want as long as it's the same. If we want to be able to get an approximate answer, and usually we do, because there's a lot of applications to these types of equations, then we want to make sure that we're stick with either the common log or the natural log. So I've got ln of 3 raised to the x minus 2 power equals ln of 5. Now I do this because I want to bring that exponent down in front. I want to use that property of logs that says I can do that. So now we have x minus 2 times ln 3 equals ln 5. Now, I guess algebraically there could be a couple of different ways that we could proceed, but I think I will just divide both sides by ln 3. And that gives us the equation x minus 2 equals ln 5 over ln 3, and then we just need to add 2 to both sides. Ln 5 over ln 3 plus 2. So there's the result in exact form, and then getting an approximation gives us ln 5, closing those parentheses, and then dividing by ln 3, closing those parentheses, and adding 2. 3.465. So there's our approximate answer. And then we want to check. So if we do a quick check here, 3 raised to the 3.465 minus 2 power, that's 3 to the 1.465 power. That's 5.0001. So that checks out. So this problem was a little bit more involved than the last one, just because we had we were raising 3 to the x minus 2 power. We had to do just a little bit more algebra to solve. This next one's a bit more challenging. We're going to solve this one. Notice that we have our unknown is trapped up as an exponent on different bases on both sides of this equation. So I'm going to start by taking the ln of both sides. All right, so now it looks like this. Now remember, the reason that we want to take the ln of both sides is so we can use those properties. And the primary property we're interested in is that one that says we can bring an exponent down in front. Now we could do that on the right side, but we are not ready to do that on the left side yet. That property that says that we can bring an exponent down in front, we can only do that when the entire base is being raised to that power. And on the left side, I've got a product first. So we're going to split this up using that property that says if I'm multiplying inside, I can split it up as a sum of two logs. So now I've got ln 2 plus ln of 4 to the x minus 1 power equals ln 17 to the x. Now I'm going to go ahead and bring these powers down as factors in front. So ln 2 plus x minus 1 ln 4 equals x ln 17. So now we want to solve for x, and I've got x appearing on both sides, and just like any equation, we're going to get our x's all on one side. I got to focus on what's going on right here, though. I've got x sort of trapped inside a set of parentheses, and I'm going to free it from those parentheses. I'm going to just distribute this factor of ln 4. Remember, ln 4, ln 2, ln 17, they're just constants. So I'm going to take this factor of ln 4, and I'm going to distribute it. So we have ln 2 plus x times ln 4 minus ln 4 equals x times ln 17. I think I will go ahead and just get all of my x's on the right side. That seems like it would take less work. So I'm going to subtract x ln 4 from both sides. So now we've got on the left side ln 2 minus ln 4 equals, and on this side I'm subtracting x times ln 17 minus x times ln 4. Now, what we're going to do on the left side, I'm going to focus on this here. I'm going to take a look at another example. Here's a related example. If I wanted to do the subtraction, I don't know, 12x minus 7x, we all just instinctively say, oh, I've got 12x, I'm subtracting 7x, and that leaves me with 5x, and that's absolutely correct. What we're actually doing, without writing it out, is we're saying, oh, this is 12 minus 7x. We're kind of taking that x out and then just doing the subtraction on those coefficients. And that's exactly what we're going to do here. I've got ln 17 times x minus ln 4 times x. And so this is ln 17 minus ln 4 times x. And now we can solve for x. Just divide both sides by ln 17 minus ln 4. So as an exact value, we get the fraction ln 2 minus ln 4 divided by ln 17 minus ln 4. We have to be careful about how we put this in the calculator. If you want to put it in the calculator in this form, you just have to make sure that we put parentheses over the top and parentheses around the bottom. And then also be careful to close the parentheses of each log. So parentheses, open parentheses up top, we have ln 2, close those parentheses, minus ln 4, close those parentheses, and then close the numerator. Divide, open parentheses for the denominator, ln 17, close that ln, minus ln 4, close that ln, and then close the denominator. And we get negative 0.47905. Oops, 0.5. And there's the approximation. Again, if you're more comfortable working with approximate values early on, you can do that. You could take the equation right here and rewrite it. So ln 2 is 0.69315 plus, and then x minus 1 times ln 4 is 1.3863 equals x times, and ln 17 is 2.8332. And you could solve that equation out. Just as I said before, don't round too coarsely, right? So I took each of these out like several digits. You could see, you know, when you look at this equation here that we just wrote out with those approximate values, when you take the log of both sides, you're making it, you're seeing how you're creating basically a linear equation. And we know how to solve linear equations, right? So the log is our kind of magic tool for solving these equations, turning an equation where the exponent or the variable lives in the exponent to just a linear equation that we know how to solve. All right, our next example is an application. One area in which you see exponential functions used to model problems occur in exponential decay, like carbon dating a fossil or something. So here they've given us equation. They say that the radioactive carbon-14 in an organism at the time of its death decays according to the equation given here, where T is the time in years, and A naught is the amount of carbon-14 present at the time of death. That's when we start time. So T is equal to 0 there. We want to estimate the age of the skull uncovered at an archaeological dig if 10% of the original amount of carbon-14 is still present. So what they're telling us here at the end, they're saying that 10% of the original amount is still present. They're telling us that the amount A is equal to 10% of A naught, or 0.1 times A naught. And we want to know how long it takes for that to happen. So the equation, I'm just starting with the equation they gave us that models this situation, e to the negative 0.000124t. I could tell it's an exponential decay problem. Decay problems have the negative exponent. Exponential growth problems have a positive exponent. And they're telling us that A is equal to 0.1 times A naught. So I'm just going to plug that in right there. So even if I don't know exactly how much was present at the beginning and maybe exactly how much is present now, as long as I can relate it and say, you know, I'm able to tell there's about 10% left, then this equation is still solvable because A naught is definitely not going to be 0. There was some carbon-14 at the time of death, and so that means that I can divide both sides by A naught. I am confident that that is not 0. And then we get the equation 0.1 equals e to the negative 0.000124t. And here I've got an equation where my variable is chopped up as an exponent, and we know what to do now. We're going to take a log of both sides. Now we could take any log that we want. We know that we focus on either the common log or the natural log because those are built into our calculator, and we can get nice approximate values. Because this function or this equation is written with the base e, it would be silly not to use the natural log. So if I take the natural log of both sides, I get this equation here. Now, because it's a natural log, when I plug in an exponential of base e inside the log of base e, they annihilate each other. Those are inverse functions. And so the right side is just negative 0.000124 t. And now to solve, we need only divide both sides by negative 0.000124. And now we can approximate. So ln of 0.1 divided by negative 0.000124. 18,569.23. And in this problem, they say that t is the time in years, so that's the age of this skull. Is that what it was? Yes, a skull discovered. All right, now we're going to solve some logarithmic equations. With these log equations, first we see if we have like sums and differences of logs, make sure that we sort of can condense each side if it involves multiple logs to write it as a single log. And then we're either looking at a couple of different situations. Either we're looking at the situation where I've got two logs equal to each other, and if that's true, that means that their arguments must be the same, so we could drop those logs right out of the equation. Or if it's not just one log is equal to another log, we can rewrite the equation in its exponential form. So we're going to start out with an example 519 here. We want to solve for x. X is the argument inside this log. 5 times log base 32 of x is equal to negative 3. I've got just a single log involved in this equation. So what I'm going to do first is isolate this log. And I'm going to do that by just dividing both sides by 5. So I have log base 32 of x is equal to negative 3/5. Now I'm going to take this second approach here. I'm going to rewrite this log equation in its exponential form. And that means I'm going to take my base 32, raise it to the negative 3/5 power, and that gives me the argument inside. So x is 32 to the negative 3/5 power. And I think, you know, the numbers involved here are pretty convenient actually, so we can evaluate this without a calculator. So I've got a negative exponent, so that's 1 over 32 to the 3/5 power. And a 3/5 power means we're taking the 5th root and then cubing it. And 32 is a perfect 5th power. It's 2 to the 5th, so the 5th root of 32 is 2. We get 1 over 2 cubed, and that means we get 1/8. So there it is as an exact value. Of course, right here, you know, you could plug this into the calculator and get the same result. All right, so in this equation we have logs, you know, throughout the equation. Every term is a log. And so what I'm going to do first, I'm subtracting some logs on the left side, so I'm going to condense that left side and write it as a single log. And the first thing we got to do is take care of any coefficients in front. I'm going to do that throughout the equation. So I have ln of 2x minus 1 minus ln of 4 squared, which is 16, equals ln of 2 cubed, which is 8. Now on the left side, since we are subtracting, that means I can combine those logs by dividing inside. So ln of 2x minus 1 over 16 equals ln of 8. Now the log function in general is what we call one-to-one or injective, and what that means is that if I have two logs of the same base that are that are equal to each other, so two logs are equal to each other, that only happens if the arguments are equal to each other. So applying that principle down here, if ln of 2x minus 1 over 16 is equal to ln of 8, that means that 2x minus 1 over 16 must be equal to 8. And now that's a pretty simple equation. We'll just multiply both sides by 16. So 2x minus 1 is equal to 8 times 16, which is 128. We'll add 1 to both sides. And then divide by 2. So x is 129 over 2. All right, let's try another one. Here I've got, it's really a similar type of equation. I want to solve for x. It's the argument of that log on the left side. So I've got 3 logs here. I want to condense the logs on the left side. I've got 2 logs. I'm subtracting a couple logs on the left side. I'm going to start by writing that as a single log, and we do that by putting that factor in front as a power on 3. So now I have log base 2 of 3 squared, which is 9, minus log base 2 of x equals log base 2 of 45. We're subtracting here, so we can combine that as a single log. By dividing inside. And if I have 2 logs of the same base that are equal to each other, the only way that happens is if the arguments are equal. So we get 9 over x equals 45. And now we're almost done. Let's multiply both sides by x to get it out of the denominator. So 9 is 45x. And now it's all over but the shouting. Divide by 45. So we get 9 over 45, that's 1/5, is equal to x. One thing we have to be careful of with logs is that you can't put in 0 or a negative inside the log. So whenever you're solving an equation, like a logarithmic equation where your unknown that you're solving for is inside a log in the original equation, like this is, we just do a quick check at the end to make sure that the value we found is not 0 or negative. It has to be a positive number. If we solved this and got a value that was negative or 0, we'd have to conclude that that is not, in fact, a solution to this equation that we started with. It doesn't mean that we made any mistakes. It could very well be a solution to, this new equation that we make, after we drop those logs out. But it just means that maybe there's no solution to the first equation that we tried to solve. All right, we got one more log equation to solve here. Notice here I've got a couple of logs on the left side, so I'm going to write that as a single log, and then it's just equal to a constant. There's not a log on the other side. And so this is an example of one where I would just probably rewrite it in its exponential form. This is, let's see, we're just adding a couple of logs. There's no coefficients out in front to take care of, so we're ready to just combine the left side as a single log. Since we're adding the logs, we'll multiply inside the log. Log base 2 of 5 times x plus 2 equals 4. Now, I know that log base 2 of this stuff is equal to 4, so I'm going to use the definition of the log. I'm going to rewrite it as an exponential equation. I know that 2 raised to the 4th power gives me the stuff inside. So on the left I can distribute. I get 5x plus 10. 2 to the 4th is 16. We can subtract 10 from both sides. So 5x is equal to 6. And now we just divide by 5. Get x is 6/5.